All right.
And the last thing is the participants cannot unmute themselves. So if you want to take questions in between the lectures,
okay,
you can ask them to raise their hands, and you will have to unmute the participants and then take the questions.
All right. Okay.
So I'll be in office. If you need anything, just feel free to call me.
Okay. Good. Thanks. So, like, are you still there? Or?
I'm still here. I'll be here for a few minutes after you start.
Okay. So, like, shall I wait for a couple of minutes?
Yeah, you can wait for a couple of minutes. So the start time is 2:30. It's still 1 minute till there. Yeah. You can wait for a few minutes just to let everybody in.
Yeah, yeah.
I can see there are 55 participants who have joined so far, but I'm sure a few more will join in after the session starts.
All right, let me try to share my screen then.
Yeah, so it's working. It went away now.
Is it working or?
Yes, I can see your screen share. You may want to just change a few, put it to full screen mode and change a few slides to see if it works.
Yeah.
Okay, the first slide.
Can you see the slide full
I can see the slide full screen, and this is the title slide.
Yeah.
Okay.
And let's see. Yeah.
Yes, it's changing. It's changing.
Good.
Yeah. Okay. Sounds good. I think you can feel free to start whenever you want to from here on.
Okay, so then I can just start. So without delaying further, I think 50 people is a lot. Thank you all for joining me this afternoon. So I'm Saugat Mujahid, and I'll be talking today to you about probing the dark baryons in the universe. Okay, so I'll explain what do I mean by dark baryon in a couple of slides. So the idea of this talk is to sort of give you a flavor of the type of work we do here in IUCAA. Myself and Professor Raghunath, Sri Anand, Neeraj Gupta, and their students and postdocs. But I'll just try to keep it simple as possible. And if you have any questions, I think you can ask at the end of the talk. That way, it's better for me so that I don't, because if it is a lecture in the hall, then you can quickly raise your hand and ask questions, and we can move on. But these things, I don't know how to take your questions and all. Probably I'll take at the very end, or you can also write your questions in the chat box, so that afterwards I can respond to you, or even you can send me emails with your questions or any other queries. Okay, so you can find my email ID from IUCAA webpage. Okay, that's sounds good. So let's start with this. I don't know whether you have already seen this. I'll start with this picture as the showing you the mass energy distribution of the universe, right? And according to the latest results from CMB measurements, now we believe that almost 70% of the mass energy of the universe is in the form of dark energy, and about like 27% of it is in the form of dark matter. And only about 5% is really ordinary matter which interacts electromagnetically, right? And the dark energy, it drives the accelerated expansion of the universe, and dark matter, on the contrary, actually holds the cosmic structures together. So it acts like glue, okay? Or you can think of it as a cement if you are building a multi-story building. And the baryons is the smallest portion of the universe energy matter distribution, and it's actually forms the observable universe. You, me, everything we know is actually made up of the ordinary matters. And the awkward thing here is that although we know how the dark matter and dark energy should behave, uh, we didn't detect them. They remain undetected because these dark components, they do not interact with the electromagnetic field, and therefore it has become extremely challenging to sort of say anything about them, basically. But there are indirect evidences of their presence. Okay, but today I'll be talking about somewhat different thing. I'll tell you that this 5% of ordinary matter, even not all of those baryons are visible. Okay, and about 30 to 50% of the ordinary matter at low redshift are not even accounted for. We don't know where they are. Okay, and that's equally like awkward situation. Like even those components which should be seen, we don't see them. Okay, so let's take this picture from the Eagle cosmological simulation. What is shown is that, so in the simulation, what people are trying to do using very fast computers, they are trying to sort of understand how the universe actually evolved with whatever we know from observations. Okay, and what is shown here is the distribution of gas. Okay, at redshift 0 in some part of the universe of the Eagle box. Okay, and you see that here the blue color is actually probing cool gas with temperature 10 to 4 Kelvin or so, and the green color here is color coded for warm hot gas with temperature a few times 10 to 5 Kelvin or so, and the red color is really hot gas. It's above 10 to 6 Kelvin. And you can see that the most of the volume in the simulation box is filled by the cool gas and warm hot gas. And the hot gas, the red components, are really seen at the nodes where different filamentary structures are actually merging to a point. So like here, 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 here. So they are the most dense regions in the universe. And we'll see that there are lots of galaxies and structures around them. But what I try to sort of emphasize here, that the most of the volume is filled by this cool gas and warm hot gas, and with densities of roughly 10 to minus 3 particles per cc. And these cool and warm hot gas are not directly visible, owing to their very low densities. And there have been sort of a new trend in the astronomy, how to probe this very diffuse gas, very low density gas that is forming these filaments. So trying to probe the cosmic filaments in emission, but it has been really, really challenging. So we are hoping that with the next generation telescopes, like 30-meter telescopes that India has participated in, called TMT, or the European collaboration 40-meter class telescope ELT, when come online, we'll have better understanding of those really diffuse gas in the universe that emit very, very little, and it's the surface brightness is so low. With the present telescopes, we won't be able to detect them. So that was the sort of catch behind the title of my talk, being these dark baryons. So they are there, we know, but they don't emit, and therefore we don't detect them. And if you just go to the nodes of these structures where you see lots of hot gas, And so even there, the density is low, but owing to the very high temperature, these regions will be detected in X-ray or gigahertz observations. So now I'll show you the exact part of the simulation box, but what if we just look at stars in the next slide? Okay, so it's the exact same box, but it's just the stellar light. So the light that is produced inside stars. Okay, so if you see that the most of the volume filling cool and warm hot gas, you don't see them, and only the densest part of these cosmic filaments or these structures are visible via stellar lights. But our knowledge about astronomy actually historically comes from studying stars within our galaxy and extragalactic objects like galaxies as a whole. We have been studying the stellar light for a very long time. But you see the catch here, that if you are only concentrating on the stellar light, then we may be missing a whole lot of sort of baryons or a gas that is out there with very low surface brightness. We won't be able to sort of identify or characterize what they are, their physical states and so on, and their role in structure formation. So I think that's the sort of main point of my talk. And now I'll see what observers have done. Okay, so this was like from simulation perspective. We see the issue that were not all the most of the volume filling gas that is cool and warm hot, they are not bright enough to be detected with the present telescopes. So now let's see what are the reservoirs of cosmic baryons. Where are the potential locations where these cosmic baryons can reside? So I'm saying here this observable universe is basically galaxies, the high density region, the nodes, and then IGM. This is called intergalactic medium. This is low density. So galaxies are collapsed object. Okay, and IGM is cosmologically evolving. It's following the expansion of the universe. And IGM is basically filling the most of the volume in the universe. So the variants definitely are there in IGM and inside galaxies. And when we call galaxies, galaxies are again a collection of stars in their disks. And ISM, interstellar medium with densities of 1 particles per cc. And even beyond the luminous part of galaxies, what we call the circumgalactic medium, with again very low densities like 10 to 3 particles per cc or so. So these are the potential locations where there should be baryons. And galaxies, depending upon where they are located, galaxies could be located in the field, in the fields. That means there are no companion galaxies. For example, a classic example of field galaxies is UGC 2885. It's also called Rubin's galaxy, after the name of famous astronomer Vera Rubin, who actually discovered that the stars in galaxies are moving too fast for his mass, and therefore there has to be some dark component of it, which is actually determining their motion. And that was the seminal work actually cited for the presence of dark matter in galaxies. And this galaxy is one of her sample. And it actually lives in a field. There is no accompanying galaxies at the same redshift. And galaxy can also reside in a group. For example, a classic example is Stephan's quintet. So there are 5 galaxies, 1, 2, and there are 2 here, 3, 4, and 5. It's called Stephan's quintet. So few galaxies are like a handful of galaxies that are living very close to each other. We call galaxy group. And there will be even gas in between those galaxies. So this intergroup medium. And galaxies could be can form a cluster, like for example here Able 1869, where you see hundreds of galaxies in a very small patch of the sky. And in this case, you will also you'll have to consider the gas within the cluster. It's also called ICM, the intercluster medium. So these are typically the components or sort of reservoirs where we should try to find the cosmic variance. And people have done it, like in 2012, a study led by Mike Shull is actually have done these variance sensors. And you can see that's the pie chart of it. And you see galaxies, that means your disk, the stellar mass of all the galaxies at redshift less than 0.5, it actually contributes to only about 7% to the cosmic variance. The circumgalactic medium, which is halo around the galaxies, is contributing only 5% of the cosmic variance. An intra-cluster medium, that is gas within clusters emitting a hot X-ray, hot gas emitting X-ray, that component is actually contributing 4% of the cosmic variance. And cold gas in the ISM studied, probed by H121 centimeter emission, is actually contributing to roughly 1.7. And all these paths like photoionized Lyman alpha forest, I'll come to that, what do I mean by Lyman alpha forest. And then it's called warm hot intergalactic medium, or WIM, probed by Lyman alpha absorbers, and WIM probed by O6 absorbers. So these are the measurements from the intergalactic medium using absorption line spectroscopy, which I'll come to in like few slides or so. So if you just add up this contribution that have been detected from the intergalactic medium, Lyman alpha forest, WIM Lyman alpha, and WIM O6, it contributes only 53% of the cosmic variance. And again, you see, these are like really low density region, and therefore invisible. They do not emit any detectable light. And if you just consider the collapse structures, that is galaxies and their ISMs, CGM and ICM, they contribute in total is only like about 18%. And again, the CGM contribution that we see about 5%, that part, again, it's not detected via emission, okay? So only 13% of the cosmic variance are actually detected via direct emission, okay? So there are two very interesting thing here, that 60% of the cosmic variance do not emit light, and therefore they are dark. So the question arises, like, how do we detect those variants? So I'll come to this question, how do we detect? And sorry. And and 30% of the cosmic variants are yet to be detected. You see this 29 plus minus 13, we don't know where they are. Okay, so it is generally believed that they are in the IGM itself, but they are actually shocketed to a very high temperature, and there is no diagnostic lines through which we can probe that phase. And this is called missing baryons problem. Okay, and it's unsolved for almost 2 decades. And of course, people have been searching to answer this question, where are those missing baryons? So it's still a like active field of research to sort of understand how can we explain these missing baryons. And people have been like active in trying to address this question. So seeing the invisible, so how can we detect those baryons that do not emit light, right? So for direct detection, the baryons must emit electromagnetic radiation. For example, processes like free emission or radiative decombination or collisionally excited line radiation. But the emission measure is proportional to the it goes as density squared, because it's a particle-particle interaction. And therefore, if the density is like 10 to minus 4, 10 to minus 5 particles per cc, the emission measure is really, really low. But the low density gas that does not emit much can absorb electromagnetic radiation. And that's what we will use to sort of probe those dark baryons. And optical depth for absorption can be written as n times sigma times L, where n is the density, sigma is the absorption cross section, and L is the length of the absorber. And if you multiply this n times L, we call it a column density. We call that column density times this sigma. So you can see that tau, absorption optical depth, is proportional to just density. So therefore, absorption line spectroscopy is very sensitive probe to low density gas, diffuse gas in the universe, which are otherwise invisible. We can do a little calculation. For example, absorption cross section of ionizing photons for the ground state of H1. So let's say you have 13.6 electron volt photon. So a neutral hydrogen atom. So the 13.6 electron volt photon will see a cross section of 6.3 times 10 to minus 18. And you can see that that value is roughly the Bohr radius square. Typically, it's close to that, which is not surprising though. And then like you can calculate what is the column density the gas should have in order to produce an unity optical depth, right? So you can calculate from this equation. So NH1 is 1 times sigma, since tau is 1. So it turns out to be 10 to 17.2 per centimeter square. So that should be the column density of the gas to sort of produce an E-folding decrement in the continuum flux. So you can write as I naught e to the power minus tau, and then since tau is 1, then I naught by E. So if the incident radiation or incident photon encounter a column density of 10 to 17.2, then the radiation will be absorbed 1 by E time, right? So this is the sort of this slide explains the technique that we use to probe diffuse gas in the universe. So what is happening here? You have a very bright source of continuum light far away from us. And there are these clouds, like diffuse, very low density clouds that are too faint to be detected in emission, okay? And let's say they are composed of pure hydrogen, okay? Neutral hydrogen, for example. So the light from the bright background source when coming to our telescope will be absorbed by the gas, intervening gas between you and the quasar, and then they will leave imprints as this in the spectrum of the background quasar. So for example, this is the farthest clouds, so it's actually producing a line in the very red part of the spectrum because it's getting redshifted. And then there's this somewhat nearby cloud, it's producing a line slightly in the blue wards. So x-axis here is wavelength, and the nearest cloud is again producing a line, blue wards of these two lines. And then this is the spectrum in panel D, what we will see in reality from the telescope. So I found this nice, I don't know whether it will work. So this video from the internet, and so you see, no, it's working. Okay, so you see that's the very bright source in the background, and light is actually coming from that source to you. And this is the unabsorbed continuum of this source, okay? So that's the Lyman alpha emission corresponding to that source, Lyman beta emission, and so on. And now we'll see that as the photons go through the intervening medium, depending upon the compositions in the intervening medium, it will produce absorption line at different part of the spectrum, you see. So each time it is hitting something, it is producing an absorption line. And you see that this is really an interesting case where you are really going through a galaxy disk, a foreground galaxy disk, and let's see how it goes. Yeah, so it's going away, right. So you see a very strong absorption it actually produced. We call it a damped Lyman alpha absorber. I'll come to that again later. And not only it produces H1 absorption, it also actually shows various metal line absorption, for example, carbon 4 and silicon 4 and so on. So let's see how it goes. So yeah, so then by the time the photons reach us, we'll see the spectrum something like this. Okay, so now this is the whole sort of how do I say it? Sort of a technique that we'll be using to probe this gas in the universe that doesn't emit much. Okay. Now, what are the unique features of quasar absorption line spectroscopy? So there are two things that we have to keep in mind. One is that it's a luminosity unbiased tracer of cosmic structures. It doesn't matter how luminous this intervening gas is, it will just produce absorption depending upon its composition at different parts of the spectrum. And it probes a wide variety of astrophysical environments. And as I said, like it can probe a very different. I don't see my cursor at all. What happened? My cursor is gone now. I see there are 3 posts in the chat box. I'll take those later, but I don't understand why. Yeah, got it. So yeah, so as I was saying, that it can probe a wide variety of astrophysical environments with very different densities and temperatures and metallicities and sizes. And the typical ranges are here, you can for your reference. And you can see that it's a quasar spectrum at redshift 0.1. And this is a quasar spectrum at redshift 3.6. So that's redshift 0.15, and this is roughly 3.6. And you can clearly see the difference in those two spectrum in terms of absorption. You can see a very dense absorption. We call it Lyman alpha absorption forest. Okay, here, and such dense and strong absorption is not present at low redshift in the spectrum of low redshift quasar. So what it means clearly that it actually tells you that the physical state of the intergalactic medium at high redshift and low redshift, it's very different. And in particularly the density, since the universe was like small at high redshift, so the density was quite high at high redshift compared to low redshift. And you can see that it's just so obvious just from the look at it, right? And that's why famous spectroscopist Professor Blair Savage once said, if a picture is worth 1,000 words, then a spectrum is worth 10,000 pictures. And I can assure that that's not an exaggeration. But of course, you have to be a smart spectroscopist like Blair Savage. He did some of the most interesting and pioneering works in this field. All right. So, okay, so now we see that in the quasar spectrum, there are lots of absorption. Now, how do we identify lines? Okay, so and if a line with rest frame, if I considering some line with rest frame wavelength lambda rest, and depending upon the redshift, it will be sort of redshifted to a different position in like at different wavelength. And the observed wavelength and rest frame wavelength are connected by this equation, lambda observed equal to lambda rest into 1 plus z. So if we know of two known transitions with rest frame wavelengths lambda 1 rest and lambda 2 rest, then lambda observed 1 by lambda observed 2, the observed ratio of those lines will be exactly equal to the rest frame line wavelength ratios, because 1 plus z factor will cancel out because they are coming from the same redshift. So this is the principle we use to sort of identify line. So for example, you can see the spectrum plotted in red here. Okay, so that's a line that we try to identify. And so you see this line over here in red, and similar structure have been repeated here as well.
No, Sogat.
Yeah.
Your slides are not changing.
Oh, I see. I see. That's why there are so many. Okay.
First, unshare the screen and do it again.
That's okay. Okay, sorry guys. I should have noticed your message before. Okay, so then that means, all right. Let's try again. I think that movie messed up things. Now, can you see my
line identification?
Yeah.
Not in.
So you can see it, right?
Yeah. Just change one left, right, back, forward.
And now let me just make it full screen.
Yeah, right.
Yeah. Now, can you see it?
Yeah, it's working now.
Okay. So I probably missed you guys from here. Is it changing there still?
Changing now.
Okay. So I'll probably missed you here where I lost my cursor. Okay, so let me see in the chat box. Okay, good, thank you. And I'm sorry, really sorry for this. I wasted a few minutes. Okay, so now I have to be a bit quick. So I was trying to go slow. Okay, so what I was saying is that there are two important aspects of this quasar absorption line spectroscopy. One is that it can trace cosmic structure in a luminosity unbiased way. It doesn't matter how luminous or how much light it emits, the absorbing the medium. It doesn't really care about that. And that's a really powerful tool. And secondly, it can probe a wide variety of astrophysical environments with very different densities, temperatures, metallicities, and sizes. So you can see the corresponding ranges over here that one can probe using quasar absorption line spectroscopy. Yeah. Yeah, so I was talking about Blair Savage's famous comment. He once said that if a picture is worth 1,000 words, then a spectrum is worth 10,000 pictures because it carries just so much information. And if you're really a smart spectroscopist like him, then you can actually derive 1,000 pictures without a problem from a spectrum. It's really not an exaggeration. Is it moving? Can you confirm?
Yeah, it's moving.
Okay, great. So now I was trying to tell you how we identify a line, okay? So, and the line identification technique actually relies on this simple, very simple fact that the observed line ratios of two known transition would be the same as the rest frame line ratios. For example, magnesium 2 has two doublet transition at 2796 and 2803 angstrom, okay? And you see this red spectrum here. So that's the 2796 transition from some redshift. And this other member of the doublet, it's actually falling here. It has a slightly higher wavelength, so it's redshifted a bit more, okay? Now, what I did, I actually shifted this spectrum by this ratio, this rest frame lambda 1 rest by lambda 2 rest. So we know the rest frame wavelength ratios, and I shift the wavelength array to this, and you can see now they are falling one on top of other, and it has to happen because of this condition. So once you see such matches in the spectrum, original spectrum and the shifted spectrum, then you know it has to be Mg2 absorption. And once you know that that's an Mg2 absorption, you can also calculate their its redshift. For example, the Mg2 2796 line is falling at roughly 3998 angstrom. So you can use the first equation again to calculate the redshift, and in this particular case, the redshift turns out to be 0.43. Okay, so once you identify a line, so we also have to measure sort of different parameters from the line in order to do science, and the strength of an absorption line is actually defined by something called equivalent weight. Okay. So if let's say this is the absorption line, and the area of the absorption line is here in the shaded region. Now you can draw a rectangle next to it for which the side is, one side is the height would be the height of the continuum. Here IC is equal to 1. And then what should be the corresponding width? So you just equal the area of this and this, like the rectangle and the area under the absorption line, and then you can calculate the width of this rectangle, which has the equal area of that the line. So in mathematical terms, you can write it as 1 minus I by I naught d lambda, and I by I naught is like e to the power minus tau. You can do d lambda. And if tau is really small, that means optically thin line, it's very weak line, then e to the minus x can be expanded as 1 minus tau lambda. So you can do simple calculation, then you can get a relationship between equivalent weight and sort of what we call column density. So it's, as I already mentioned, that tau is n sigma L, right? So if you just put this expression for tau here, then you'll get n and times sigma d lambda, and then you can approximate as the mean absorption cross section sigma 0 times the bandwidth of the over which the line is detected. And you can clearly see that if the tau lambda is really small, then the equivalent weight is proportional to column density. Okay, so that's easy. So if you know the equivalent weight, if you measure the equivalent weight, you can get the column density pretty easily from a weak ine. But in principle, you can express this absorption cross section in terms of like sigma 0 times phi lambda, and phi lambda is called broadening function, and sigma 0 is coming from quantum mechanics with this symbols with their standard meaning, where GU and GL is the statistical weights and AUL is the transition probability of that transition, right? So moving on, so let's say the sigma lambda is sigma naught into phi lambda, where phi lambda is the broadening function, And there are a few mechanisms that actually through which a line, one can broaden a line. So the first of all is the natural broadening, and it follows from the fact that the lifetime of the excited state is finite, and therefore this delta E times delta T, according to Heisenberg uncertainty principle. So your the energy, the delta, how do I say it? The energy level that you are talking about cannot be infinitely sharp, but there will be uncertainty in that. So that means it's actually broadening your line. And secondly, the thermal broadening, and it follows from the fact that atoms are not in rest, and it has some temperature, and when there is temperature, they will move like with some velocity, and that's the dominant broadening mechanism, at least in the case of IgM or in the CGM. And also there can be like pressure broadening, or also called as collisional broadening, because the gas, the absorbing medium, has finite density, and so there will be collision with other atoms and ions to the atoms that is emitting, and that will also like give you a broadening. So this natural and pressure broadening, they have a characteristic shape called Lorentzian, and it actually can be written as like this, where gamma is called damping constant or damping factor, where x is in units of lambda or frequency or wavelength. And the thermal broadening will have a Gaussian shape with, as you all know, again x here is either a frequency or wavelength, and the intrinsic shape of a line will be the convolution of these two, like a Gaussian function and Lorentzian function, and the resultant function is called void profile. And what we observed in reality will be again this void profile convolved with the LSF meaning the line spread function of the instrument. And it follows from the fact that the line is observed with an instrument which have a finite resolution, okay? And again, you have to convolve with that the profile of line spread function of the instrument that you are using to observe that line. So that's that. And here you can see the void profiles, the shape of the void profiles for different sigma and gamma values. And here the red and blue curve are the two sort of asymptotes where it's actually taking a Gaussian shape for black line and pure Gaussian, and it's taking pure Lorentzian shape for the red line. You see that Lorentzian profile has a stronger wing compared to Gaussian profile. Moving on. So once you observe a line and then you fit a profile, like for example, void profile to that, then you will derive another quantity called the line width, or we express it as B parameter we also call. And this Doppler parameter can be sort of, can have contribution from thermal and non-thermal contribution. And you can write it as B square is B thermal squared and B non-thermal squared, where B thermal is basically square root of 2 kT by m, where m is the mass of the atom that you are talking about. And you can express it as 12.8 kilometers per second, square root of T4 divided by MA, where T4 is temperature in units of 10 to the power 4 Kelvin, and MA is the atomic mass number. So for example, for hydrogen, it's 1. And let's say you have a gas purely of hydrogen, which is at 10 to 4 Kelvin, then the thermal width of your line would be 12.8 kilometers per second. And BNT, which is called non-thermal broadening, we don't know. It will depend upon where you are actually, where you are looking at. But if you have two lines that is coming from the same gas, then you can write this equation, B square and B thermal square plus B non-thermal square, as like this. B1 square is 2 kT by M1 and plus BNT square, and B2 square is this. Then you have basically two equations and two unknowns. Unknowns are temperature and non-thermal broadening. So if you have two lines from two different elements with masses m1 and m2, in principle you can solve for temperature and non-thermal broadening or turbulence in the medium, which is really cool. So now moving forward, so I'm again coming back here, this equivalent weight relation. Equivalent weight, as we have already seen, can be expressed as this equation, and tau lambda is like n sigma 0 times phi lambda d lambda. So phi lambda is the broadening function, which can be approximated as void profile. So now if you do this calculation properly, and then it is possible to find a relation between equivalent width and column density for a whole range of equivalent width, okay? And not, the line doesn't have to be really weak. And we have already seen that if the line is really weak, then equivalent width is directly proportional to the column density. But if you really solve this equation without any approximation, then you can actually find a relation between equivalent width and column density, and that relation is known as curve of growth, which is shown here. In y-axis is log W and x-axis is log NH1. So this curve of growth is done for Lyman alpha line, but you can do it for any line you want. Okay, and you can see there are three distinct regions or paths of the curve of growth. One is this region, where it's called linear part, where equivalent width is proportional to n, as we have already seen. If the tau is very, very small, so that's the optically thin region. And as the line is becoming strong, so that's the line you see here is a column density of 10 to 13. So that's the weak line we are talking about here, like when we are talking about this linear part of the curve of growth. And as the line becomes stronger, it actually falls in the logarithmic or flat part of the curve of growth, where equivalent width is proportional to b square root of log n by b, where b is the Doppler parameter that we discussed in the last slide. And square root or damping part, when the line is even stronger, so then it goes to here, where the equivalent weight is proportional to the square root of column density, like this. And you can see that when the line is in this region, you can see a very prominent wing of this absorption line. So this is called the curve of growth, and we use curve of growth in a regular basis in order to sort of calculate the column density or measure column density from a spectrum. And for Lyman alpha line, you can derive that the column density would be 1.8 times 10 to, okay, now again I see lots of chats. That means my slide is not moving. Now there is no gas. Thanks for pointing this out. I'm just, let's see, escape. No. Okay. Let me try again. I'm really sorry. I don't know where exactly I missed you guys. Share screen. Share. No. Yeah, can anyone confirm, like, can you see the cursor now? Okay. 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 I got it. Not visible. Yeah, I see that is when it was not full screen, we could see it. Okay, but Okay. Yeah, let me try again. Now even I cannot see the cursor. Not good. Yeah.
What happened? Cursor issue?
Yeah, cursor issue. I don't know.
Just go full screen.
Yes.
Share your screen.
Yeah, they notice that when I'm going full screen, they can't see it anymore.
Okay.
Going full screen. Can you see my cursor?
No.
What happened?
Then don't go with the full screen.
Okay. Okay. So that's what I'll do. Probably I'm losing too much time. Share screen. You see my screen, right?
Yeah.
Can you see the cursor?
Yeah. Okay, fine. This is not problem. You can teach.
All right. Okay, so now you can see my cursor. Okay, I don't know what I was saying. sorry. This is really should not happen. Okay, so I was talking about the curve of growth, and I was talking about the three parts of it, like the linear part and flat part and the damping part. And at different parts, the equivalent weight is related to column density differently. Okay, and the relationship is actually shown here at different parts. And for Lyman alpha line, if we just consider Lyman alpha transition, then NH1, the column density of a neutral hydrogen or Lyman alpha, column density would be 1.84 times 10 to minus 14 per centimeter square times the rest frame equivalent weight, if the line is in the linear part of the curve of growth, like here. For example, if the rest frame equivalent weight of Lyman alpha line is like 100 milliangstrom, then the column density would be 2 times 10 to 13 per centimeter square. And again, so here you can see that there is a degeneracy between this relation and its equivalent weight and column density. It's not directly related because there are additional dependence on the B parameter. Okay, you see this. So for example, this profile is for a column density of 10 to 15, but with a B parameter or Doppler parameter of 13 kilometers per second. Now, as you increase the Doppler parameter, you see it looks so different. Okay, so when the line is in the flat part of the curve of growth, it's really difficult because of this degeneracy to extract the right column density for such transitions. But anyway, once you are in the damping part again, so you can see damping part, if the your line is in the damping part, it will clearly show a wing, a very prominent wing in the absorption like this here. And again, when your line is in this part, there is a unique relation between equivalent weight and column density. And for Lyman alpha line, this relation takes this form: 1.88 times 10 to 18 per centimeter square times the equivalent weight squared. Okay, and if the rest frame equivalent weight of a line is like 10 angstrom, that would correspond to a column density of 2 times 10 to 20 per centimeter square. And this is a very sort of important number for us, because that's where we call an absorption or Lyman alpha absorption damped Lyman alpha absorber. So for column densities above that value, like 2 times 10 to 20. All right. And now, so the types of quasar absorbers. So now we see that we can, from quasar spectrum, we can detect absorption line, we can determine their redshift, we can measure their equivalent weight, and from that equivalent weight, with the help of curve of growth, we can estimate column densities. And then depending upon the column densities, or depending on the absorption column density, H1 column density in particular, quasar absorbers are classified into 3 categories. One is called the Lyman alpha forest absorbers with column densities less than 10 to 17.2 per centimeter square, and that's when the line is falling in the linear or in the flat part of the curve of growth. And then Lyman limit absorbers or LLS, when the column density is more than 10 to 17.2 per centimeter square, that's when the line is in the flat part. And if you remember, at this 10 to 17.2, this column density came one of my earlier slides, where we are doing this in the optical depth equation. We put tau equal to 1, then what is the corresponding column density, and that's that. Okay, so this 17.2. So I did it purposefully because we know that we'll come back to it. And then third categories is called, just I introduced, damped Lyman alpha absorbers, where the line is falling in the damping part of the curve of growth with a column density greater than 10 to 20.3. Okay, and so this is a schematic, very crude, to sort of tell you where one should expect such types of absorbers. So let's say this is my galaxy. You can think of it as a Milky Way or anything, and the red part is the size of the disk, and the green circle is the sort of what we call circumgalactic medium. That's the extent of the sort of its dark matter halo, okay, so to speak. And now if you are really far from a galaxy with megaparsec scale, and you have a quasar sight line, and you took the spectrum of that quasar, so then it's actually probing intergalactic medium, okay, low density, and that's when you will encounter column densities of few times 10 to 13, few times 10 to 14. And those are the clouds you see that produce lots of absorption line in the spectrum of the high redshift quasar. So, and as you go like closer to a galaxy, like from megaparsec scale to, let's say, a few hundred kiloparsec scale, then naively one would expect that the column density, neutral hydrogen column density, will also increase because the density is increasing around your any galaxies basically. And so when you are at a 100 kiloparsec scale, you will see strong Lyman alpha forest absorption and Lyman alpha limit systems with column densities 10 to 17.2. Okay. And this Lyman limit the term comes because it produces unity optical depth in the continuum, and that's why you see a break in the continuum of the background quasar because of such absorbers. And if we're really close to a disk or within the virial radius of a galaxy, like let's say within few tens of kiloparsecs, if your sight line is going through. Then as we already seen from the movie as well, when the sight line was going through a galaxy, you really see a very strong absorption. And that's when you sort of expect to detect damped Lyman alpha absorbers with very high column densities. Okay, it's not very sort of it's not the accurate description. It's not that every time you are going through 100 kiloparsecs from galaxy, you will see Lyman limit or so, but it roughly gives you the idea. Okay, so when the column density is small, you can think that you are actually quite far away from galaxy. Okay, but it's need not be true always. Okay. All right, so I think I used up all my times, and sorry guys for these mishaps with my cursor and the other thing. I don't know what happened, but maybe I'll take 5 more minutes if you are still there. Okay. Yeah. So now I was trying to I aimed at to tell you what we have been doing, or I have been doing here in IUCAA. So my main research interest is to probe the immediate vicinity of galaxies using quasar absorption line spectroscopy. And it's actually demonstrated by this figure. It's taken from a recent review on circumgalactic medium. So you see, that's the disk size of a Milky Way mass galaxy. So you know that Milky Way is like 15 kiloparsecs. So that's 15 kiloparsecs here, okay? But the virial mass is like a few times 10 to 12 solar mass for Milky Way mass galaxy. And that means the virial radii, the dark matter halo size would be like up to 200 or 280 or even 300 kiloparsecs. So if we are sitting outside of Milky Way and looking at Milky Way, so this is the luminous part we'll see with a decent telescope. Okay, but there are lots of gas around Milky Way itself. For example, there are Magellanic streams, Magellanic clouds, low mass galaxies, and hundreds of dwarf galaxies that are embedded within the Milky Way halo. And those things we won't see when we are far away from Milky Way, sitting in deep space. Okay. So we are doing the reverse experiment. We are looking the extragalactic sources, galaxies, and using quasar absorption line spectroscopy to probe diffuse gas in this medium. And why do we want to do that? Because we want to understand how this luminous part of the galaxy or disk basically the galaxy is interacting with their surrounding. And what do I mean by that is like, how do galaxies get their gas from the intergalactic medium? Because otherwise galaxy won't form stars, like if there is no material falling in. And you know that when there are gravity, it will just attract more material into it. And it's not that it only accretes and forms stars when at the end of the stellar phase, it's like blow gas from the disk because of supernovae explosion, or when they form stars, a coherent burst of star formation called a starburst. Even then they drive lots of materials out in the CGM or even in the IGM. So we want to address this, we want to understand these processes. And as I said, like these things are actually involved with diffuse gas. They don't emit. So it's very, very difficult to probe these processes directly. So that was our whole sort of my research interest, that I want to address, or I try to understand these processes that actually drives galaxy evolution. And for this, I'll just skip these things. We are using the very large telescope in Chile. Is the European Union. I think you probably know about VLT ESO. It's a collection of 4 8.2 meters telescopes. So we are using data from this telescope, and that's one of the largest telescopes in the world. Okay, other one being the Keck from United States. And we are using a very interesting spectrograph, and it's very new. It's called MUSE, Multi-Unit Spectroscopic Explorer. So in conventionally, either you take image or you take a spectrum, okay, of a extragalactic source or anything in the sky. But with MUSE, you can do the two things at the same time, basically. So you can take the image and at the same time you get the spectrum, and that's really, really powerful. And one MUSE field, like MUSE, we call cube, is like 1 arcsecond by 1 arcsecond, the field of view, and with a spatial sampling of 0.2 times 0.2 arcseconds, that's the spaxel size. That means within that it contains about 90,000 spectra, so each MUSE cube, okay, and that's really, really remarkable, okay, and it's actually changing the field in a drastic way. So we are using this MUSE data to do our surveys, and you see in one of the surveys that I'm leading at the moment, it's called MUSE Cubes, MUSE Quasar Field Blind Emitter Surveys. We have 8 MUSE fields centered around a bright quasar. For example, here, it's one of the fields, that's the MUSE data. And at the center, there is a quasar. So this quasar, we took another instrument, again on VLT, to get a very high signal to noise ratio, a high resolution spectra of this. And then we use this MUSE observation to find galaxies around these quasars. So we know galaxies, and we know background quasar, and then we study the sort of absorption spectra at the redshift of the quasar. So at the redshift of the foreground galaxies. For example, here you have we detected a Lyman alpha emitter at redshift 3.08. And then we looked at the corresponding, because you know that lambda rest is 1 plus z times, lambda observed is 1 plus z times lambda rest. So that's the redshift we got from Lyman alpha emission. So that's the galaxy. And then we are looking for carbon 4 absorption in the quasar spectrum. So where we should look at is 1 plus z times the redshift of the galaxy. And we see strong Lyman alpha and carbon 4 absorption. So we have a huge sample of such absorption and galaxy pairs. So we're trying to study them statistically. So I won't take any longer. So I think just to tell you that it's a really new sort of field, and we are using state-of-the-art instrument, and we have huge amounts of data that people would be dying for to work on. And actually those data to be analyzed and published excellent science. And if you are still there, I can hope that you are really interested in observational science. And if you do have interest, then welcome. I think you should apply for a PhD position at IUCAA, because we need youngsters like you. So that's all. Thank you very much for your attention. Now I think we have 2 more minutes. If you want to ask question, I'm happy, but otherwise I can take chat box. Yeah, I'm really bad at dealing with this thing, it seems. Okay, let's stop share. All right. Maybe a time of 1 or 2 quick question. Anyone? If not, then I can just say, okay, let me see.
Hello, sir.
Yeah.
Am I audible?
Yes, yes.
So can you please go back to that last slide?
Last slide. Okay. Okay, I have to share it again.
Yes.
This one or?
The previous one.
This?
No, actually, the one where you showed the. Yes, this one.
Yeah, yeah.
So the the two images at the two extreme corners, they are. I mean, what's the significant difference between the two? Can you please elaborate on that?
Okay, sorry, I didn't get enough time to explain this. Yeah, so that's the Muse field, okay, here. And as I said, that each pixel we have a spectrum which is covering between 4,750 to 9,350 angstrom.
Right.
And here we have identified, you cannot see anything in the white light image where we collapsed all the wavelengths here because they are really faint in continuum emission, okay?
Mm-hmm.
So you don't see anything, but when you look at the right wavelengths, so what we did, we ran a match filtering technique where without even it can peak the lines at a different wavelengths basically, okay? So it doesn't have to be visible like this. For example, here you can see low redshift galaxies, they are clearly seen in continuum, but these structures, they are really low mass galaxies and therefore not seen in the Muse continuum. But if you go to the right wavelength, you will see emission line. So that's what it is. So it's called narrowband image. So you are making image using only those wavelengths where the line is detected, and that's how it looks. Okay. So once you know that there is a galaxy there, you can calculate the redshift because you see the emission line, let's say here. So that's the emission line corresponding to this galaxy, which is at wavelength about 4,960 angstrom or so. So then, and we know that this is Lyman alpha. And then you divide by the rest frame of Lyman alpha minus 1. So that's redshift 3.08 is the redshift we get. And so that's one galaxy. And here again, we found another galaxy. Again, it's the narrowband image, and that's the 1D spectrum. And from this spectrum, we calculated the redshift of this galaxy to be 2.93. Okay. So so that way we are building catalog of foreground galaxies, and then we are trying to see their signatures, the absorption signatures in the spectrum of the background quasar. Is that clear enough?
Yes, sir. Yes, sir. And sir, one last question. And that distance what is written at the bottom of those two images, 176 kiloparsec and 171 kiloparsecs. So, does that indicate the galactic width, or is that the depth from that plane of observation?
Yeah, so that's the distance from the quasar. Okay.
Oh, okay, okay.
As I was showing you that if your galaxy is here and you are looking far away from galaxy, what type of absorption you would see. So that's that. So it's the separation between the quasar and the galaxy. Because galaxy is here. I don't know if you can see my cursor.
Yes, I can see it.
Yeah. So galaxy is here. And we are probing its halo or the diffuse gas around them far away from that galaxy. Okay, so that's the measure of how far your galaxy is. So it's like 171 kiloparsec. Okay, so as I showed you in one of my cartoon thing here, for example, you see. So that's the distance I was talking about. So if you are like hundreds of kiloparsecs, so you are more likely to see strong Lyman alpha forest absorption or Lyman limit system absorption. Now you go back to here. So that's the Lyman alpha absorption coming from this galaxy. So you see, it's not super strong, but yeah, it's really saturated Lyman alpha absorption. You see.
Oh, okay, okay.
So now the what we try to see how the gas is distributed around galaxy. So we'll make a plot in x-axis distance from the quasar and y-axis what is the column density of neutral hydrogen, or what is the equivalent weight of neutral hydrogen that we measured in the spectrum of the background quasar. So and then we can construct a profile, and that will give us an idea how this diffuse gas are distributed around galaxies, and that's a very important quantity to sort of observe or measure. Yeah. So.
Oh, okay, okay. Yes.
Yeah.
Thank you.
Thanks. So I think you have next lecture in 15 minutes. But if you have any question, you can send me an email to my IUCAA email ID, and then I can try to answer you if you have any remaining questions. All right. Thank you, guys. Thank you for your attention. And I'm really sorry for these mishaps that happened with Zoom. Yeah. All right.